Hello, in this lecture I will answer two questions. In the first question, we find out the size of this angle x, and in the second question, we find out the area of this green shape. So we start with the first question. In the drawing, we have a quarter circle. A or B is a quarter circle. Therefore, this is angle A or B. This is a right angle. In addition, we know that angle APQ is also equal to 90 degrees in size. We also know that AB equals to PQ. Again, our test is to find out the size of angle PQB is equal to x. We have to find out the value of angle x. So first of all, we will complete the quarter circle to a semicircle. So we completed the quarter circle to a semicircle. We define this point as point M. So actually AM is the diameter of this semicircle according to our construction. AM is the diameter of the semicircle. Repeat again, AM is the diameter of the semicircle according to our construction. We completed the quarter circle to a semicircle, and therefore AM has been the diameter of the semicircle. So AM is the diameter, it is absolutely a straight line. So if we focus on the right side of the straight line AM at point O, here the sum of the angles must be equal to 180 degrees. According to rule 3, that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AM at point O? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we'll extend line segment PQ by straight line until it touches the semicircle. But the question is, where the extended line segment PQ will touch the semicircle. We will assume that the extended line segment PQ will touch the semicircle at this point, point L. And therefore, we have here peripheral angle APL is equal to 90 degrees in its size according to what is given in the question. And peripheral angle APL subtend on chord AL. Again, peripheral angle APL subtend on chord AL. but chord AL is definitely not the diameter of the semicircle. Why? Because it doesn't pass from point O, that is the center of the semicircle. And you know that the diameter of any circle or a semicircle must pass from the center of the semicircle. AL is not doesn't pass through the center of the semicircle, therefore AL is not the diameter of the semicircle. So here we have contradiction to rule 5. Well, because according to rule 5, any peripheral angle that is equal to 90 degrees in its size, like this peripheral angle APL, must subtend on the diameter of the semicircle, but AL is not the diameter of the semicircle. So if we click on rule 5, according to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. So in the drawing we have a circle. This is peripheral angle AOB. That is equal to 90 degrees in size, and therefore peripheral angle AOB subtend on AB. That is the diameter of the circle. So according to this rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. But here we have peripheral angle APL that is equal to 90 degrees in size, and it subtend on AL that is not the diameter of the circle, and therefore that is not the diameter of the semicircle, and therefore it is contradiction to rule 5. So we can set the option that peripheral angle AP and that the extended side PQ will touch the semicircle at point L. So in the next step, we will assume that the extended line 7 PQ will touch the circle at this point H. Repeat again, we will assume that the extended line 7 PQ will touch the circle at point H. So we have peripheral angle APH that is equal to 90 degrees in size, and it subtend on chord AH. Again, according to our assumption, the extended line segment PQ will touch the circle at point H, and therefore we have peripheral angle APH that is equal to 90 degrees in its size, and it subtend on AH. But again, we have contradiction to rule 5. Why we have contradiction to rule 5? Because AH is definitely not the diameter of the semicircle. Why AH is not the diameter of the semicircle? Because AH doesn't pass from point O, that is the center of the semicircle, and therefore AH is not the diameter of the semicircle. So we have a peripheral angle APH that is equal to 90 degrees in its size, and still it doesn't subtend on the diameter of the circle because AH is not the diameter of the circle. So we have again contradiction to rule 5. So due to the contradiction to rule 5, we will have to conclude that the extended side PQ will touch the semicircle at point M and not in any other point. Again, due to the contradictions, we will have to conclude that the extended side PQ will touch the semicircle at point M and not in any other point. Now we don't have any contradiction to rule 5 because of the fact that we have peripheral angle APM that is equal to 90 degrees in its size, and indeed it subtend on AM that is the diameter of the semicircle exactly according to rule 5. So in the next step we'll join points A and Q together by straight line. By joining points A and Q, we created the right and associated triangle, triangle APQ. Triangle APQ is the right angle because angle APQ is right angle, and it is also an associated triangle because AP equals to PQ. And we have the rule that in front of equal sides in the triangle there are equal angles. So if we relate to the right and associated triangle, triangle APQ, in front of those two equal sides, side AP equals to side PQ according to what is the Green's equation. So in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in the right and associated triangle APQ must be equal to 180 degrees. So which angles we have in the right and associated triangle APQ? We have this angle that is the right angle. Alpha plus alpha is 2 alpha, so 90 degrees plus 2 alpha equals to 180 degrees. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. Here we subtract 90 degrees from this equation and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So here we divide this equation by 2 and get that angle alpha equals to 90 degrees over 2 is 45 degrees. So if this is angle alpha, that equals to 45 degrees in its size. And this is also angle alpha, that equals to 45 degrees in its size. In the next step, we will prove that those two right angles can go into each other according to side angle side rule. That is to say, we will prove that the right upper triangle AOQ can go into the right lower triangle OQM. So why those two right triangles can go into each other? So I write it down. We will prove that the right upper triangle AQM, AQO, the right upper triangle AQO can go into the right lower triangle OQM. So, why those two right triangles can go into each other? First of all, AO equals to OM. They're above the radii of the circle, therefore they are equal to each other. They're above the radii of the semicircle, therefore they are equal to each other. So we define the radius of this semicircle as R, so AO equals to R, OM also equals to R. So repeat again, if you found out that AO side AO of the upper right triangle AQO is equal to side OM of the lower right triangle QOM, above the radii of the semicircle, therefore they are equal to each other. In addition, those two angles are both right angles, therefore they are equal to each other. So angle AOQ in right triangle AOQ is equal to angle OQM in the right triangle OQM. They are both equal to 90 degrees. Repeat again. Angle AOQ in the right triangle AQO in the right triangle AQO is equal to angle OQM in the right triangle QOM. They are both equal to 90 degrees and they are both equal to 90 degrees and therefore they are equal to each other. And finally, this is side OQ. This is a common side that belongs to both triangles. So you can write down that OQ equals to itself is a common side that belongs to both triangles. Repeat again. Side OQ equals to itself is a common side that belongs to both triangles. So if we prove that those two right angles can go into each other according to side angle side rule. So I write it down. If we found out that the upper right triangle AOQ congruent, this is the sign of congruent, to the lower right triangle OQM according to side angle side rule. That is to say, if we found out that those two sides and the angle that is included between those two sides in the right upper triangle AOQ are correspondingly equal to those two sides and the angle that is included between those two sides in the right lower triangle OQM. Therefore, those two right angles can go into each other according to side angle side rule. And for the fact that those two right angles can go into each other, we will derive that side AQ of the right triangle AOQ is equal to side QM of the right triangle OQM. And again, we derive that side AQ of the right triangle AOQ is equal to side QM of the right triangle QOM. According to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other in their lengths. So if we found out that side AQ equals to side QM. So if we relate to the big associated triangle AQM, triangle AQM is an associated triangle because AQ equals to QM. So in the big associated triangle AQM, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. So in the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is actually rule 8. According to rule 8, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. Again, according to rule 8, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. So in the drawing, we have triangle ABC that could be any triangle. Those two angles, alpha, beta, and gamma, they are both defined. They are all defined as interior angles because of the fact that they are located inside triangle ABC. While this is angle ACF that is located outside triangle ABC, and therefore it is defined as an exterior angle. So angle ACF that is equal to E according to our definition is defined as an exterior angle. So the size of this exterior angle E is equal to the sum of the two interior angles that are not adjacent to it. This is the interior angle gamma that is definitely adjacent to angle E. The two other interior angles that are not adjacent to it are those two angles alpha and beta. So the size of angle E equals to alpha plus beta, because they are the two interior angles that are not adjacent to it. So according to rule 8, this rule 8, the size of the interior angle E is equal to the sum of the two interior angles that are not adjacent to it. That is to say, it is equal to alpha plus beta. So we can actually implement rule 8 in our drawing. One, because in our drawing, we have the associated triangle, the big associated triangle AQB. Those three angles are defined as interior angles. This is angle AQB that is defined as an exterior angle of triangle AQB because it is located outside the associated triangle AQB. So according to rule 8, the size of the exterior angle AQB will be equal to the sum of the two interior angles that are not adjacent to it. This interior angle AQM is definitely adjacent to angle AQP. The two other interior angles that are not adjacent to it are those two angles, beta and beta. Therefore, the size of the exterior angle AQP must be equal to beta plus beta. So if we relate to the big associated triangle AQM, according to rule 8, the size of this exterior angle AQP is equal to the sum of the two interior angles that are not adjacent to it. That is to say, it is equal to beta plus beta. Repeat again. If we relate to the big associated triangle AQM, the big associated triangle AQM, according to rule 8, the size of the exterior angle AQP is equal to the sum of the two interior angles that are not adjacent to it. That is to say, it is equal to beta plus beta, that is 2 beta. So the size of the exterior angle AQP is equal to 2 beta, according to rule 8. But we already found out that the size of the exterior angle AQP is equal to 45 degrees. So we can substitute angle AQP by 45 degrees. So 45 degrees equals to 2 beta. Here we will divide this equation by 2 and finally get that the missing angle beta is equal to 45 degrees over 2, that is 22.5 degrees in its size. So if we found out that the size of this angle beta is equal to 22.5 degrees, this is also angle beta that is equal to 22.5 degrees in its size. In the next step, we focus on the right triangle OQM. In the lower right triangle OQM, the sum of the angles must be equal to 180 degrees. So which angles we have in the right lower triangle OQM? We have this angle, this is the right angle, plus this is angle beta that is equal to 22.5 degrees in its size, plus this missing angle OQM. In total, the sum of those three angles must be equal to 180 degrees. Which again, in the right triangle OQM, the sum of the angles must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So 90 degrees plus 22.5 degrees plus the size of the missing angle OQM, in total it must be equal to 180 degrees. Here we subtract 90 degrees from this equation and we get that 22.5 degrees plus the size of the missing angle OQM, in total it must be equal to 180 degrees minus 90 degrees is 90 degrees. So 22.5 degrees plus the size of the missing angle OQM, in total it must be equal to 90 degrees. Here we subtract 22.5 degrees from this equation and we get that angle OQM, the size of the missing angle OQM is equal to 90 degrees minus 22.5 degrees is 67.5 degrees. So she found out that the size of this missing angle OQM is equal to 67.5 degrees. We have the rule that says that vertex angles are equal to each other. And we have the rule that says that vertex angles are equal to each other. So actually, those two angles alpha and beta are defined as vertex angles and they are equal to each other in their sizes. So this is to say alpha equals to beta. Likewise, we have another pair of vertex angles, angle 1 and angle 2 are also defined as vertex angles, therefore they are equal to each other. That is to say, angle 1 equals to angle 2 in its size. So we can implement the rule in our drawing. Because in our drawing, we have those two angles that are defined as vertex angles and they are equal to each other in their sizes. So angle X equals to 67.5 degrees in its size. So if you know that the angle that we are working for in this equation is angle X is equal to 67.5 degrees in its size. And that is the answer to the question. And again, the size of angle P cubed is equal to X is equal to 67.5 degrees in its size. So we finish with the first question. In the next step, I present to the second question and solve the second question of this lecture. In the second question, our task is to find out the area of this green shape. So, in the drawing, we have a semicircle. PQ is the diameter of this semicircle that is equals to 10 units in its length, therefore the radius equals to 5. In addition, we know that inside this big semicircle we have the big square ABCD and we have the small square MEFC. Again, our task is to find out the area of this green shape. So first of all, we define the center of this semicircle. This point is point O. We join points O and A together by straight line. OA is the radius of this semicircle that is equal to 5 units in its length. Again, the radius of this semicircle equals to 5 units in its length. So actually half the diameter. We join points O and D together by straight line. OE is of course the radius of this semicircle is equal to 5 units in its length. This is square MEFC. In any square, all the angles are right angles, therefore this angle is a right angle. Likewise, in the big square ABCD, this angle is also a right angle. We will define the length of one side of square ABCD as A, so AB equals to BC equals to CD equals to BA equals to A. We define the length of this short line segment OC as X. So what is the length of the missing line segment BO? From the dominant it's very easy to see that BO equals to BC minus OC. So it is known BO equals to BC minus OC. So BO equals to BC that is A minus OC that is X. So in total we found out that BO equals to A minus X units in its length. BO equals to A minus X units. In the next step, we define one side of this whole square MEFC as B, so EF equals to B and CF also equals to B. So in the next step, I'll copy the big right triangle ABO in a new page and we will implement on the big on the right triangle ABO the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the motion for Pythagoras theorem. Actually, this is the right triangle ABO that they come from the original drawing. This right triangle ABO, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. So, if I write it down, this will be equation 1. According to equation 1, AO squared, that is the square of the hypotenuse, is equal to AB squared plus BO squared. AO is 5, therefore AO squared is 5 squared, that is 25. And it is equal to AB squared. AB is 8, therefore AB squared is A squared plus BO squared. BO equals to A minus X, therefore BO squared equals to A minus X squared. So in total, according to equation 1, we found out that 25 equals to A squared plus A minus X squared. In the next step, I'll copy the right triangle OEF in a new page and we'll implement on it the Pythagoras theorem. Here by PT is the information for Pythagoras theorem. The hypotenuse O equals to 5 units in its length. This is also the radius of the semicircle. EF equals to B units in its length. And side OF in total equals to X plus B. So actually this is the right triangle OEF that I copied from the original drawing. In this right triangle OEF, according to the Pythagoras theorem, this will be question 2. According to the Pythagoras theorem, OE squared, that is the square of the hypotenuse, is equal to EF squared plus OF squared. OE is 5, therefore OE squared is 5 squared, that is 25. And it is equals to EF squared. EF is B, therefore EF squared is B squared plus OF squared. OF equals to X plus B, therefore OF squared equals to X plus B squared. So in total, according to equation 2, we found out that 25 equals to B squared plus X plus B squared. This is according to equation 2, while according to equation 1, we only found out that 25 equals to A squared plus A minus X squared. In the next step, we get equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. And again, we get equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. According to equation 1 equals to A squared plus A minus X squared. And it must be equal to 25 according to equation 2. 25 according to equation 2 equals to B squared plus X plus B squared. According to equation 3, we found out that A squared plus A minus X squared equals to B squared plus X plus B squared. Here we'll open the brackets on both sides of this equation 3. Find out that according to equation 3, a squared plus a minus x squared. A minus x squared equals to a squared plus x squared plus 2 times a times x. And it is equals to b squared plus x plus b squared. X plus b squared equals to x squared plus b squared plus 2 times x times b. So here we have x squared on both sides of this equation 3, so x squared will get cancelled. After we cancel x squared, in the side of the equation 3 we left with a squared plus a squared, that is 2a squared minus 2ax. And it is equal to b squared plus b squared is 2b squared plus 2bx. Here we will divide this equation 3 by 2, and you get that 2a squared over 2 is a squared, minus 2ax over 2 is ax, and it equals to 2b squared over 2 is b squared, 2bx over 2 is bx. So in total we found out that a squared minus ax equals to b squared plus bx. Here we add ax to this equation 3, and we get that according to equation 3, a squared equals to ax plus bx plus b squared. So here we'll subtract b squared from this equation 3, and we get that according to equation 3, a squared minus b squared equals to ax plus bx. So according to equation 3, a squared minus b squared equals to ax plus bx. So here we take x out as a common factor from those expressions, so inside the brackets we left only with a plus b. We found out that according to equation 3, a squared minus b squared equals to x times a plus b. Here we have the famous algebraic identity that says that a squared minus b squared equals to a plus b times a minus b, and it is equals to x times a plus b. A and b are the legs of square, the big square and the small square. A is the length of the big square, one side of the big square, and b is the length of one side of the small square. Therefore, there are positive numbers, and when you add two positive numbers to each other, the result must be a positive number. Therefore, a plus b is a positive number, and therefore it is allowable to divide this equation 3 by a plus b. Because of the fact that a plus b can never be equal to 0, it must be a positive number. So we divide this equation 3 by a plus b. So here a plus b will get cancelled, and we left only with a minus b. Here a plus b also will get cancelled, and we left only with x. So in total, according to equation 3, we have found out that a minus b equals to x. Here we will add from this equation 3 b, and we get that a equals to x plus b. According to equation 3, a equals to x plus b. Here we subtract x from this equation 3, and we should find out that according to equation 3, a minus x equals to b. A minus x equals to b. So here we will square this equation 3, that is to say, we square both sides of this equation 3, and get that a minus x squared equals to b squared. And again, according to equation 3, we found out that a minus x squared equals to b squared. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape in total, it is equals to the area of the big semicircle minus the area of the big square ABCD minus the area of the small square MEFC. Repeat again, we found out that the area of this green shape is equal to the area of the big semicircle minus the area of the big square minus the area of the small square. What is the area of the big semicircle? The area of any semicircle equals to pi r square over 2. That is to say, the area of the circle over 2. Therefore, the area of this big semicircle must be equal to pi r square over 2. But we already found out that the radius of this semicircle r equals to 5. If r is 5, therefore r squared is 5 squared, that is 25, so pi r squared over 2 is 25 pi over 2. So we found out that the area of this semicircle equals to 25 pi over 2 square units in its size, minus the area of the big square ABCD. According to our definition, the length of one side of this big square ABCD equals to a. Therefore, the area of this square ABCD must be equal to a square. So it is minus a square minus the area of the small square. One side of the small square is b, therefore the area of the small square is b square. So it is minus b square. So in total, we found out that the area of the green shape, that is the area that we are looking for in this question, it is equals to 25 pi over 2. That is the area of the semicircle minus a square minus b square. That is the area minus the area of the big square minus the area of the small square. So the area of the green shape in total equals to 25 pi over 2 minus a square minus b square. Here we take out minus 1 and second factor from those two expressions. So inside the brackets we have a square plus b square. So in total we found out that the area of the green shape equals to 25 pi over 2 minus a square plus b square. But according to equation 1, we have only found out that 25 equals to a square plus a minus x square. But again, according to equation 1, we have only found out that 25 equals to a square plus a minus x square. And we have only found out actually that according to equation 3, a minus x squared equals to b squared. And again, according to equation 3, we have only found out that a minus x squared equals to b squared. Therefore, we can substitute a minus x squared in this equation 1 by b squared from equation 3. We'll do it now, and we'll get that according to equation 1, (25) equals to a squared plus a minus x squared. A minus x squared according to equation 3 is b squared. So we substitute a minus x squared by b squared. So in total we found out that according to equation 1, a squared plus b squared equals to 25. Again, according to equation 1, a squared plus b squared equals to 25. Therefore, you can substitute a square plus b square in this expression for the green shape by 25. Repeat again, we substitute a square plus b square by 25, because a square plus b square equals to 25 according to equation 1. So we do it now, and we get that the green shape in total equals to 25 pi over 2 minus a square plus b square. But a square plus b square according to equation 1 is 25. So we substitute a square plus b square by 25. So in total, we have found out that the green shape that is there that we are looking for this equation, there of this green shape, is equal to either 25 pi over 2 minus 25 square units, or in terms of numbers, the value of this expression is 14.27 square units in its size. Repeat again, we found out that the area that we are looking for in this question, that is there of this green shape, is equal to either 25 pi over 2 minus 25 square units in its size, or in terms of numbers, the area of this green shape equals to 14.27 square units in its size. So we finish with the second question. In the next step, we summarize the lecture. We start with the first question, of course. In the first question, our test was to find out the size of this angle x, is actually angle PQB, is equal to x. We have to find out the value of angle x. So in the domain, we have a quarter circle, AOB is a quarter circle, therefore this is angle AOB, this is a right angle. In addition, we know that angle APQ is also a right angle, and AP equals to PQ. Again, our task is to find out the size of this angle, angle x. So, in the first step, we completed the quarter circle to a semicircle. Therefore, AM is the diameter of the semicircle according to our construction. Again, because of the fact that we completed the quarter circle to a semicircle, AM must be the diameter of the semicircle. Again, AM is the diameter of the semicircle according to our construction. So AM is the diameter of the semicircle, this is absolutely straight line. So if we focus on the right side of the straight line AM at point O, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at the right side of AM at point O? We have this angle, this is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we extended line segment PQ by straight line until it touches the semicircle. But the question is, well, the extended line segment PQ will touch the semicircle. We assume that the extended line segment PQ will touch the semicircle at this point L. So according to our assumption, we have here line segment APL, this is equal to 90 degrees in its size, and line segment A. We have the peripheral angle APL. Peripheral angle APL is equal to 90 degrees in its size according to what is given as the equation. And peripheral angle APL subtend on chord AL. Again, peripheral angle APL subtend on chord AL. But chord AL definitely is not the diameter of the semicircle. Why? Because it doesn't pass from point O. That is the diameter. That is the center of the semicircle. And we know that the diameter of any circle or semicircle must pass for the center of the semicircle, and therefore AN cannot be the diameter of this semicircle. So we have a contradiction to rule 5, because we have because we have peripheral angle APL that is equal to 90 degrees in its size, and still it doesn't subtend on the diameter of the semicircle. It subtends on AL that is definitely not the diameter of the semicircle. And according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the semicircle. But AL is not the diameter of the semicircle. So we have contradiction to rule 5. Therefore, it is impossible that the extended line segment PQ will touch the semicircle at point L. So we cancel this option, and Our second option will be that the extended line segment PQ will touch the semicircle at point H. Will touch the circle at point H. So we have, according to our assumption, we have peripheral angle APH. Peripheral angle APH is equal to 90 degrees in size according to what is given in the question, and it's subtend on AH. Peripheral angle APH subtend on AH. But AH is definitely not the diameter of the semicircle because it doesn't pass for point O. For the AH doesn't pass for point O. Therefore, AH is not the diameter of the semicircle. So we have here contradiction to rule 5 because peripheral angle APL must subtend on the diameter of the semicircle because it is equal to 90 degrees in size. So due to the contradiction to rule 5, we have to conclude that the extended line segment PQ will touch the semicircle at point M and not in any other point. Why? Because now we don't have any contradiction to rule 5 because we have peripheral angle APL that is equal to 90 degrees in its size, and indeed it's subtend on AM, that is the diameter of the semicircle, exactly according to rule 5. So the extended line segment PQ must touch the semicircle at point M and not in any other point. We join points A, in the next step we join points A and Q together by straight line. By joining points A and Q, we created the right and associated triangle APQ. The right and associated triangle APQ, the sum of the angles must be equal to 180 degrees. And we have also the rule that in front of equal sides in the triangle there are equal angles. This gives us the equation that AP equals to PQ. So in the right and associated triangle APQ, in front of those two equal sides, we have those two angles that must be equal to each other. According to the rule that I mentioned, that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. We know that the sum of the angles in the triangle is equal to 180 degrees. So in the right triangle APQ, 90 degrees plus alpha must be equal to 180 degrees. So 90 degrees plus alpha equals to 180 degrees. Here we subtract 90 degrees from this equation and found out that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. Here we divided this equation by 2 and found out that alpha equals to 90 degrees over 2, that is 45 degrees. So this is the angle alpha that is equals to 45 degrees in size, and this is also angle alpha that is equals to 45 degrees in its size. In the next step, we prove that those two right triangles can go into each other according to side angle side rule. That is to say, the right upper triangle AOQ can go into the right lower triangle OQM according to side angle side rule. So why those two right triangles can go into each other? First of all, side AO of the right triangle AOQ equals to side OM of the right triangle OQM, because they are both the area of the circle, therefore they are equal to each other. In addition, those two angles are both right angles, therefore they are equal to each other. And finally, OQ is the common side that belongs to both angles. So we can write down that OQ equals to itself as a common side that belongs to both angles. So we shall prove that those two right angles can go into each other according to side angle side rule. So if it again, we shall find out that the right upper triangle AOQ congruent, this is the sign of congruent, to the right lower triangle OQM according to side angle side rule. That is to say, I shall prove that those two sides and the angle that is included between those two sides in the right upper triangle AOQ corresponding equal to those two sides and the angle that is included between those two sides in the right lower triangle OQM. Therefore, those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we derive that side AQ of the right triangle AQO is equal to side QM of the right triangle OQM. And again, we derive that AQ equals to QM according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other in their lengths. In the next step, I presented you a new rule and implemented the new rule in our drawing. The new rule is rule 8. So according to rule 8, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. So in the domain we have triangle ABC that could be any triangle. Those three angles alpha and beta and gamma are defined as any triangles because they are located inside triangle ABC. While this is angle ACF, that is equal to E. Angle E is defined as an triangle because it is located outside triangle ABC. And according to this rule 8, the size of the triangle E is equal to the sum of the two triangles that are not adjacent to it. This is the angle gamma that is definitely adjacent to angle E. The two other triangles that are not adjacent to angle E are those two angles, alpha and beta. So according to this rule 8, the size of angle E is equal to the sum of the two triangles that are not adjacent to it. That is to say, it is equal to alpha plus beta. So the size of angle E equals to alpha plus beta. So in the next time we implemented the new rule in our drawing. If we relate to the big associated triangle AQM, those three angles are defined as triangles, and this is angle AQP that is defined as an triangle because it is located outside the associated triangle AQM. And according to rule 8, the size of the triangle AQP is equal to the sum of the two triangles that are not adjacent to it. This is angle AQM that is definitely adjacent to angle AQP. The two other triangles that are not adjacent to this angle are those two angles. And therefore, the size of the triangle AQP is equal to beta plus beta. That is the size of the two triangles that are not adjacent to angle AQP. And again, according to rule 8, if we relate to the big associated triangle AQM, according to rule 8, the size of the triangle AQP equals to beta plus beta. That is 2 beta. So again, the size of triangle AQP equals to 2 beta. But we already found out that angle AQP equals to 45 degrees inside. So we can substitute angle AQP by 45 and get that 45 equals to 2 beta. Here we divided this equation by 2 and found out that the size of angle beta is 45 degrees over 2, that is 22.5 degrees. So actually this is angle beta that is equals to 22.5 degrees in size, and this is also angle beta that is equals to 22.5 degrees in size. We have the rule that so in the next step we will focus on the right triangle OQM. On the right triangle OQM, the sum of the angles must be equal to 180 degrees. So which angles we have in the right triangle OQM? We have this angle that is the right angle, this is angle beta that is equal to 22.5 degrees in size, plus this missing angle OQM. In total, the sum of those two angles must be equal to 180 degrees. So repeat again, in the right triangle OQM, the sum of the angles must be equal to 180 degrees. That is to say, 90 degrees plus 22.5 degrees, plus the size of the missing angle OQM. In total, they must be equal to 180 degrees. Here we subtract the 90 degrees from this equation and find out that 180 degrees minus 20 degrees is 90 degrees. So 90 degrees equals to 22.5 degrees plus the size of the missing angle OQM. Here we subtract 22.5 degrees from this equation and find out that the size of the missing angle OQM is equal to 90 degrees minus 22.5 degrees is 67.5 degrees. So we found out that the size of this missing angle OQM is equal to 67.5 degrees. In the next step, I presented to you the rule that says that vertex angles are equal to each other. Those two angles, alpha and beta, are defined as vertex angles and therefore they are equal to each other. That is to say, angle alpha equals to angle beta. Likewise, we have the other pair, those two angles also defined as vertex angles and they are equal to each other. That is to say, angle 1 equals to angle 2 in its size. So we can implement the new rule in our drawing. Well, in our drawing, we have those two angles that are defined as vertex angles and therefore, according to the rule that I mentioned, they are equal to each other. That is to say, angle x equals to 67.5 degrees in size. So again, in total, we found out the size of the missing angle x equals to 67.5 degrees in its size. So we finish with the first question. This is the missing angle PQB. This is equals to x. The size of this missing angle x equals to 67.5 degrees. So we finished with the first question. In the next step, I presented to the second question, and we solve the second question of this lecture. In the second question, our test is to find out the area of this green shape. So in the drawing, we have a semicircle. PQ is the diameter of this semicircle that is equal to 10 units in itself. Therefore, the radius must be equal to 5. Inside this big semicircle, we have the big square ABCD and we have the small square MCFE. Again, our task is to find out the area of this green shape. So first of all, we define the center of this semicircle. This point is point O. We join points O and A together by a straight line. Point O is the center of the semicircle. Point A is a point on the semicircle itself. Therefore, OA is the radius of this semicircle. This is equal to 5. Likewise, we join points O and D together by a straight line. OE is also the radius of the semicircle. This is equal to 5. In the next step, we defined one side of this big square ABCD as A. So AB equals to BC equals to CD equals to DA equals to A. ABCD is a square, therefore this angle is right angle. Likewise, MEFC is also a square, therefore this angle equals to 90 degrees. We define one side of this small square as B, therefore EF equals to FC equals to CM equals to ME equals to B. And we define the length of this short line segment OC as X. So what is the length of OB? OB equals to BC minus OC. Again, OB equals to BC minus OC. So OB equals to BC, that is A, minus OC, that is X. So in total, OB equals to A minus X units in its length. In the next step, I copied the right triangle ABO in a new page, and we implemented the Pythagoras theorem on this right triangle ABO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle ABO that I copied from the original drawing. Again, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right triangle ABO, the hypotenuse is AO, therefore the square of the hypotenuse is AO square, and it is equal to AB square plus BO square. Then again, AO square equals to AB square plus BO square. AO is 5, therefore AO square is 5 square, that is 25. And it is equal to AB square. AB is A, therefore AB square is A square plus BO square. BO is A minus X, therefore BO square is A minus X square. So in total according to equation 1, we actually found out that 25 equals to A square plus A minus X square. In the next step, I copied the right triangle OEF in a new page and implemented the Pythagoras theorem on this right triangle OEF. The hypotenuse OE equals to 5 units in its length. This is also the radius of the semicircle. EF equals to B units in its length, and OF in total equals to X plus B. So this is the right triangle EOF that I got from the original domain. This right triangle EOF. OE squared, that is the square of the hypotenuse, equals to EF squared plus FO squared. OE is 5, therefore OE squared is 5 squared, that is 25, and it is equals to EF squared. EF is B, therefore EF squared is B squared plus OF squared. OF is X plus B, therefore OF squared equals to X plus B squared. So in total, according to equation 2, actually found out that 25 equals to B squared plus X plus B squared. This is according to equation 2, and according to equation 1, we have already found out that 25 equals to A squared plus A minus X squared. In the next step, we created equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. Repeat again, we created equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. 25 according to equation 1 equals to A squared plus A minus X squared, and it must be equal to 25 according to equation 2. 25 according to equation 2 equals to B squared plus X plus B squared. So in total, according to equation 3, we actually found out that A squared plus A minus X squared equals to B squared plus X plus B squared. Here we open the brackets of both sides of this equation, equation 3, and actually found out that according to equation 3, A squared plus A minus X squared. A minus X squared equals to A squared plus X squared minus 2A times X. And it is equal to B squared plus X plus B squared. So it is B squared plus X plus B squared. X plus B squared equals to X squared plus B squared plus 2 times X times B. So here we have X squared on both sides of this equation. So X squared will get cancelled. After we cancel X squared, this side of the equation we have A squared plus A squared, that is 2A squared, minus 2ax equals to b square plus b square is 2b square plus 2x plus 2bx. So in total, according to equation 3, we found out that 2a square minus 2ax equals to 2b square plus 2bx. Here we divided this equation 3 by 2 and finally found out the 2a square minus 2 is a square, minus 2ax over 2 is ax, and it is equals to 2b square over 2 is b square, and 2bx over 2 is bx. So in total, according to equation 3, we found out that a square minus ax equals to b square plus bx. Here we added ax to this equation, equation 3, and finally found out that a square equals to ax plus bx plus b square. Here we subtracted b square from this equation, equation 3, and found out that according to equation 3, a square minus b square equals to ax plus bx. So a square minus b square equals to ax plus bx. Here we took out x as a common factor from those two expressions, so inside the brackets we left only with a plus b. So we found out that a square minus b square equals to x times a plus b. We have the famous algebraic identity that says that a square minus b square equals to a plus b times a minus b, and it is equals to x plus x times a plus b. A and b are lengths, and therefore they are positive numbers. And when you add two positive numbers to each other, the result must be a positive number. So a plus b must be a positive number. Therefore, it is allowable to divide this equation 3 by a plus b, because it can never be equal to 0. So we divided this equation 3 by a plus b. So here a plus b will get cancelled, we left only with a minus b. Here also a plus b also get cancelled, and we left only with x. So in total, we found out that according to equation 3, a minus b equals to x. Here we added to this equation 3 by b, and finally found out that a equals to x plus b. Here we subtracted x from this equation, equation 3, and finally found out that a minus x equals to b. According to equation 3, a minus x equals to b. Here we squared both sides of this equation, equation 3, and finally found out that a minus x squared equals to b squared. Again, according to equation 3, and we found out that a minus x squared equals to b squared. What else is to find out? They have this green shape. So what is the of the green shape? The of the green shape equals to the of the big semicircle minus the of the big square minus the of the small square MEFC. But again, the of the green shape is equal to the of the big semicircle minus the of the big square ABCD minus the of the small square. What is the of the big semicircle? The area of any semicircle equals to the of the circle over 2. That is to say, it is pi r square over 2. But we have already found out that the radius r of this semicircle is 5. Therefore, r square is 5 squared, that is 25. So pi r square is 25 pi over 2. So the of the big semicircle equals to 25 pi over 2 square units in its size, minus the of the big square ABCD. One side of square ABCD is a, therefore the of square ABCD is a square. So it is minus a square minus the of the small square. One side of the small square is b, therefore the of the small square is b square, so it is minus b square. So in total, we found out that the of the green shape equals to 25 pi over 2 minus a square minus b square. So it is 25 pi over 2. And here we took minus 1 as a common factor from those two expressions. So inside the brackets we have a square plus b square. So in total, we found out that the area of the green shape equals to 25 pi over 2 minus a square plus b square. But according to equation 1, we already found out that 25 equals to a square plus a minus x square. Well, according to equation 3, we already found out that a minus x square equals to b square. So we can substitute a minus x square in this equation 1 by b square from equation 3. Because a minus x square equals to b square. We did it, and we actually found out that according to equation 1, 25 equals to a square plus a minus x square. And a minus x square according to equation 3 is b square. So we substitute a minus x square by b square. So in total, we actually found out that 25 equals to a square plus b square. So we can substitute a square plus b square in this expression by 25, because a square plus b square equals to 25. We did it, and we actually found out that in total, the area of the green shape is equals to 25 pi over 2 minus a square plus b square. A square plus b square equals to 25 according to equation 1. So in total, we should find out the area of the green shape equals to 25 pi over 2 minus 25. In terms of numbers, 25 pi over 2 minus 25 is 14.27 square meters. So in total, we should find out the area of the green shape, that is the area that we are looking for in this question. It is equal to either 25 pi over 2 minus 25 square meters in its size, or in terms of numbers, the area of this green shape is equal to 14.27 square meters in its size. Okay, thank you very much.